So in a Byte 1981 issue, they cover the National Computer Conference that was held on May 4th in Chicago. I think it's so interesting to see people looking with amazement at these things that we consider so old now. And notice that big old Apple logo in the back. So you can find this issue and article on archive.org. Here I'll be reading Build an Unlimited Vocabulary Speech Synthesizer. So this looks interesting. So it starts, the alarm clock that jolts you out of sweet dreams with a monotone buzz is a thing of the past. State-of-the-art technology is the clock that prods you out of slumber with a voice that speaks your own language. The time is 6 o'clock. The artificial voice is becoming an increasingly important and potentially indispensable part of the interface between man and machine. Electronic speech synthesis is a young but rapidly evolving technology. It won't be long before that speaking alarm clock will also announce your entire day's appointment schedule. It will be no less unusual for the computer in your car to recount its mechanical ills as you drive to work. For now, however, electronic speech synthesis is still a relatively new concept. I'm going to skip that part. He says a speech processor based on the National Semiconductor digitalker chipset was an attempt to introduce personal computer users to artificial speech. Considering the response it received, I believe many of you are now listening to everything your computer has to say. This month, I wish to return to the topic of computer-controlled electronic voice synthesis and introduce you to the Votrax SC01 speech synthesizer chip. Instead of waveform digitization or linear predictive coding, the SC01 uses a phoneme synthesis, which allows the SC01 to speak in unlimited vocabulary simply by sequentially pronouncing the individual phonemes. These are basic sound units that make up words in the English language. Many other articles have been written that describe in detail the theory of the phoneme synthesis and the workings of the Votrax SC01 integrated circuit. I'm thinking about the irony of me not being able to pronounce the thing that describes basic sound units. When he says a few appropriate references are given at the end of this article, instead of discussing many theoretical concepts at length in my limited space here, I prefer to concentrate on the design of a practical, computer-controlled, phonetic speech synthesizer. This month's construction project shown in Photo 1 is called the SweetTalker Speech Synthesizer. It uses the SC01 integrated circuit to allow, and I assume that's going to say synthesis, of an almost unlimited vocabulary, limited only by the size and complexity of the controlling program running on the computer. The SweetTalker circuit contains I/O, signal buffering, a clock oscillator, an audio filter, and an amplifier. The circuit board provides protection from static electricity for the SC01, in addition to being a convenient package. Protection for the SC01 is important because it is both expensive, $70, and delicate. It's made using complementary metal oxide semiconductor technology. The standard SweetTalker synthesizer can be connected to any microcomputer through a parallel port, while a special version of the unit can be plugged into the I/O bus of the Apple II computer. So we have three major techniques presently used to synthesize the human voice: format synthesis, linear predictive coding, LPC, and waveform digitization. They differ in the number of bits of data required to construct a word. Interesting, number of bits. Format synthesis is essentially an electronic modeling of the natural resonances of the human vocal tract. Bands of resonant frequencies in the vocal spectrum, called formats, are generated by excitation sources and then pass through variable filters. One variation of the formant technique is called phoneme synthesis, in which the spectral parameters are derived from basic sound units that make up words. A phoneme generator circuit is used to produce these sounds. In such a circuit, each phoneme is given a numeric code, and the synthesizer circuit, discrete or integrated, utters phoneme sounds, corresponding to codes it receives when it is activated. Words and sentences are assembled by simply stringing the phoneme codes together. The electronic voice so generated is intelligible, but has a slight mechanical quality. Continuous speech using phoneme synthesis can typically be generated with a data rate of less than 100 bits per second. Okay, before reading the next type, let's check out the picture, and of course we'll read the caption. So pause here if you really want to soak this in. It says the assembled SweetTalker, a phonetic speech synthesizer circuit board. It supports a vocabulary limited only by the size and complexity of the computer program that controls the SweetTalker. Any English word may be constructed from phonemes, the basic building blocks of speech, and the circuit board shown is a prototype of the parallel port version of the SweetTalker. The Apple II plug-compatible version is not shown. Okay, so here's the chip, Votrax. 22 pin. We have some nice branding here. As before the development of the SC01, Votrax used many medium-scale integrated circuits and discrete components to perform the same functions. All these components were mounted in modules such as the VSL type shown, and when this particular synthesizer card was purchased 3 years ago, the price was $600. Compare this both in size and price to the $70 SC01, which is sitting on top here. Linear predictive coding is similar to phoneme synthesis in that both techniques are based in the frequency domain and use similar hardware to model the vocal tract. The quality of the speech is often better than phoneme or phoneme synthesis, but a higher data rate, 1200 to 2400 bits per second, is needed for continuous speech. And we have waveform digitization. It is the third method of speech synthesis in which the amplitude characteristics of a vocal waveform are stored and reproduced. The quality of speech is better than the other two methods, but the data rate for continuous speech is very high, and storing efficient amounts of data conveniently can be a problem. Various schemes of compressing the data have been devised. One of the more successful is used in the National Semiconductor digitalker system, which I described in my June Circuit Seller article. Okay, so you can pause if you wanted to read specific information about the chip. I want to move on though. There are some diagrams here. So just a scroll, a slow scroll, so you can get a sense of what this looks like up close. I want to zoom in though on the picture. So here we are. And it says the SweetTalker phonetic speech synthesizer board can be driven through any parallel output port. One port which can be used is a Centronics compatible parallel printer port. When using the connection, phonemes for words to be spoken are transmitted using LPrint statements in BASIC. Pictured above is the SweetTalker board combined with its power supply and connected to a TRS-80 Model 3 computer and speaker. So that's the article on speech synthesis, something I'm sure people are eager to get AI to do. And this is so fascinating. Here we have a list of useful words with their Votrax notation phonemes for ease in program coding. So it's so interesting to look through this and make connections like that. I wonder how many total words they have here. Now I'm curious, whatever happened to this? Down here we have our LPrint. In this particular article, it just keeps going. Well, here's the conclusion. What can you do with a computer-controlled speech synthesizer? I'm sure you have a few ideas. In any case, the benefits of electronic speech synthesis will surely propagate as more people learn how to use it. All right, thank you, Steve Sierkia. Man, the number of things I've probably mispronounced in an article about computers pronouncing things is quite a bit, so sorry about that.